Better. Okay. Okay. So yeah, again, if you can hear me, drop a comment of any sort in the chat. I'll just to say hi so you can get a sense of who's here. Um, dun-dun-dun. Yeah. How big is my audience? One, two, three, four. Okay, cool. Okay, so this is a talk about KZG commitments. Before I try to say too much about KZG, let me talk a little bit about hash functions first, which is kind of the source of it. Um, So for those of you that can in the chat, um, can someone tell me if anyone happens to know, like roughly what is the purpose of a hash function? Like SHA-256, like what does a hash function do? Okay, that's fine. All right, I guess I have to define a hash function. All right, so the purpose of a hash function, yeah, irreversible function that turns info into a string of 256 bits, for example. So if you've been on the internet for long enough and you see like these very long hex codes that appear with like, so a typical hex code will take like a message of any length, this is some message, and it will turn it output a certain like byte string of like 256 bits. So um, I don't know. And I think for the purposes of this talk, let me say that there's sort of two properties that we want these hash functions to have. One is that they should be hiding, meaning that given the output, it's hard to guess. It's hard to guess the input, and they should be binding in the sense that um, no two inputs can give the same output. Uh, give same output, and so you can think of this as the hash function, sort of like the digital equivalent of an envelope, where if I have a message and I put an envelope and seal the envelope, um, well, first the envelope hides the message so that someone can't read the message without opening in the envelope, and it's also binding in the sense that once I seal something inside the envelope, um, I can't, there's no way that I can change it. Like if once I have committed to a hash, so these things are also called hash commitments. Um, it prevents you from kind of changing the message, so to speak. So let me give a toy example of this, which is like how to play rock paper scissors over text message. But you can imagine if you have a friend and you're trying to play rock paper scissors over text message, there's a problem where like there's text messages don't show up instantly on the other person's side, et cetera, et cetera. So if you try to send someone, let me not use text message. Let me use like snail mail. I think that will snail mail. Where you have like a very slow communication channel and you would like to, rock, paper, scissors. So the way that you can use a hash function to do this thing is you can say like, okay, we're going to draw two people. I think the tradition is to call these people Alice and Bob, where Alice will pick a choice of thing and say like, it's like scissors, and also so we'll take the message scissors and then also some random bits like 0, 1, 0. It doesn't really matter what these bits are. And then compute the hash of the message, which is some hex string, and send it to Bob. So again, you can kind of think of a hash function as an envelope that you put that like seals the message inside so that Bob can't read it. but it's committed. So once Bob has the hash in his hands, like Alice can't change the message that she originally wrote. And then you can imagine Bob does something like the same thing, sends some hashed message, paper or whatever. And then once each person is holding the other person's commitment, then they can reveal the message that they originally had. And then Bob can look at this message, compute the hash, and verify that Alice hasn't changed what she originally showed. Alice can do it the other way, and then it's great. As a less trivial example, which is actually used in practice, if you're running like some sort of web server, I don't know how to draw a web server, right? Just pretend this is a computer of some sort. Yeah, recording's fine. Then
Recording in progress.
Okay. Okay. If this is a recording, let me briefly say what's happened so far, which is I'm trying to describe a thing that's called a hash function, which is a precursor to the KZG commitment. A hash function has two really important properties. One is that it's hiding, meaning that when you hash a message, it's impossible to recover what the message originally was, but it's binding in the sense that it feels injective. So if I reveal like an input that gives a certain hash, you can be convinced that that was the input that it originally had. So one way they can work with this is if you have a server and you have a bunch of users and the users each have their passwords. The one thing you're never supposed to do when you run an internet server is to store people's passwords in plain text, because then anyone who's like looking at the database in the server just learns everyone's passwords. I think like Ed Vista's found this out the hard way in the past or something like that. What you're always supposed to do is instead of storing the hash of the instead of storing the password, what you do is you hash the passwords that the user gives you and store those instead. So if your password was say correct horse battery staple, you store a hash of this password instead, and then this is some string like 137A94. So it's some 32-bit string. And this way, if someone, finds the server and can read all the memory in it, they can't learn any of the passwords because all they can see is the hash of the password. If you only see a hash of the password, then it doesn't tell you anything about what the original password is. And then when a user wants to authenticate, in order to prove that they are who they are, what they do is they tell the server, this is my password. The server computes the hash and verifies that it matches the hash that's in the database. And then that's how you can do user authentication. So store only this in database. Okay, cool. Before I go on, does anyone have any questions about like what the purpose of a hash tip function is, what it does, etc.? Oh, okay. All good. All right. Cool. At this point, I should mention something. If for the people who are really mathematicians in the room, they might be freaking out right now because what I've told you is that I want this function to be binding and collision resistant. And if you look at the hash function as a function, the the domain of the function is like any message. So it's the infinite space of all possible messages. And the output space is F2 to the 256 or whatever. It's like the bits of length 256. And if you're a mathematician, you're looking at this and you're like, this isn't an injective function. What are you talking about? Like you have an infinite domain and like, a finite codomain. Like we have this thing called the pigeonhole principle. It tells you that this function like this can't possibly be injective. And you're technically correct. The problem is that the issue of this in cryptography, 2 to the 256 is so big that it might as well be infinity. Like what we just say is like, okay, like it's not literally injective in the sense that it's injective as a function, but it's injective for all practical purposes in the sense that for all the standard hash functions published, nobody has yet been able to find an example of two messages that give the same hash. I think that's true for SHA-256. It wasn't until very recently where the like SHA-1, which is like a very old hash function that was published a long time ago, found people were able to get collisions to that function. I think Google spent like a lot of money finding this example of two PDF files that have different content but the same hash, and it was like a really big thing. But everything SHA-256 and later in practice is injective. It's not injective like officially in theory, but it's good enough. That's fine. Um, Let me give one more example of a use of a hash function that will help me motivate what's about to come with KZG, which is that you have a person who claims to be really good at predicting the stock market, all right? And they want to prove to you that they're really, really good at predicting what stocks are going to go up. So you can imagine like, they're say, I am the best person at predicting these and I will sell you my predictions. And then someone wants to say, okay, well, how do I know if your predictions are any good? So naively, you have this problem. I need an, let's give this person a name. Does someone want to suggest a name for someone who's good at predicting stock markets? Someone give me any name. Warren Buffett pops. Okay. Those are some choices. We'll call them Warren, all right? Warren. And so you're kind of so there's Warren wants to convince you that he's really good at making predictions, but he really doesn't want to give you any of his predictions for free. So he's like, I'll give you a prediction for $100, and I don't do free samples. And you're like, okay, but then how do I know your predictions are any good? And what Warren can do is you can say, okay, we'll do SHA-256 of he'll predict whatever's tomorrow, and he's like, tomorrow, I don't know, alphabet goes up 18.9%, thanks, or something. And he publishes this hash somewhere on the internet, wherever he wants, which is some, again, hidden string. You can't. So when you just see this hash, you don't know anything. And then the next day, after, Alphabet goes up 18.9%, which I don't think it will, that would be really incredible. But if it really happened, then Lauren reveals the preimage to the hash, and it proves that he made this prediction before the stock actually went up. So this is another example of a way you can use a hash. Again, the point of a hash is that it's both binding and hiding. But there's a thing where, maybe you want to do this for a long time, or you want to do this projection for like a lot of different stocks. And the problem with a straight up hash function is that it's like quite brittle in the sense that there's no way that I can reveal just a part of the message or like reveal just the thing of it. So if I want to convince you, if I give you this hash and I want to convince you that my pre-image contained the words alphabet goes up, for example, there's no way to do this other than just reveal the entire message. So the hash function is kind of an all or nothing proposition. It's like either I reveal the entire input string that I fed into the hash function, or that's it. That's the only thing you can do. So what is a KZG commitment and why do I care about it? So the KZG commitment is something that has the same properties as a hash in that it accepts as input. I should tell you the input type. A KZG commitment accepts a polynomial as an input rather than a string. So now we're going to actually make this a little more mathy. Rather than messages, which I've said are strings up until now, a KZG commitment takes input polynomials and it produces a hash communicate P, which is a number from 0 to Q. So at this point, I will tell you, right, I probably shouldn't use this notation without defining it. So when I write FQ, this is the set of integers mod Q. Yeah, this is the set of integers mod Q. You can add and divide. And Q for this talk will be, let me check my notes. Do I use Q or P in my notes? I use Q, cool. Q is going to be a prime, and it's going to be a big prime. It's going to be about like 2 to, you can think of Q as being about 2 to 256. So rather than outputting like, I guess earlier I called them hex strings. Now we're actually going to make them numbers. So I'm going to make them numbers mod Q. And like before, it's going to be binding, meaning that once I make this commitment, I can't change it. And it's going to be hiding, which means that if I just give you the commitment, it doesn't tell you anything about the polynomial. But the thing that makes a KZG commitment special is that it also has the following power, which is that I can take any set of input points in FQ. For example, we could say like 0, 1, up to like 1,000. And I can open the commitment at only those points, meaning that I will tell you the values of P of 0, P of 1, up to P of 1,000. And I'll be able to prove to you that these were the correct values. So it's kind of a lot like you can imagine it as like instead of just one envelope, you actually have like an envelope for every input point where I can open the commitment at just that input point. And this has the following properties. One is that the still doesn't tell you anything else except those values. So I'll be able to open the commitment at these points and you'll know the values at these points, but not the other ones. You don't learn any coefficients of p other than, I guess, p of 0, because p of 0 is the constant coefficient. You don't learn anything about what p of 1001 is, and so on. And most incredibly, the proof length, when I give you a proof of this, the length of the proof is exactly 256 bytes. So it doesn't matter if I open the commitment at 1,000 numbers or a million numbers. The length of the proof that I give you that my openings are truthful is always a single 256 bit number. Sorry, it should be bit, not byte. So this is the thing that makes this commitment scheme like really, really powerful, which is like not only can I do partial openings, which you completely can't do with hash functions before, but the partial openings, like I have to send you what those values are. But once I've sent you the values, I can convince you those values are correct with a single proof of length O of 1, like a constant length proof, regardless of the number of points that I'm opening it at. So that's the sort of the advertisement for this talk. This is what, by the end of this talk, I'm going to have outlined for you a procedure that lets you commit an entire polynomial, only open the polynomial at some of the points and not others. And no matter how many points I open the commitment at, I'm only going to have a constant length proof. So I'm going to pause here for any questions. This is the statement of the thing that I'm going to be trying to do during this talk. Are there any questions about what I'm claiming that I'm going to be able to do? All right. All right. Yeah. Either I've lost everyone or I'm moving too slowly and I'm not sure which one it is. But yeah, can I get any messages in the chat? Just like, am I making sense so far? Or like, is there anything in particular you want me to elaborate on? Or like, all right, all good? Uh, Probably. You're good so far? Okay, cool. Uh, okay, yeah, the virtual talks is always like this. Okay, so the piece of technology that I'm going to use in order to make this commitment possible is, for those of you in the chat, how many of you have heard the words elliptic curve before and have some idea what it's supposed to do? Fermat. Fermat? That one theorem. Oh, Fermat's last theorem. Yeah, that's a that's a very advanced. Well, it's actually a little. You need modular forms as well for that. Okay. All right. I'll give the abridged version then. So for our purposes, let me decide which curve I want to use. Okay, here's what I'm gonna do. We're gonna let P be a prime, and P is a specific prime, but I'm not gonna say which prime for now. And what I'm gonna do is I'm gonna consider the set of all solutions to the equation y squared equals x cubed plus 3 mod P. All right. Um, so if I imagine drawing this, and I hesitate to call it the xy plane because I'm taking things mod P, but bear with me, we're gonna draw the picture as if it was like an xy plane. You get a curve that looks like this, all right? Something to this effect. And then you have some points on the curve, for example. Actually, why don't I make sure the audience is wait? Can anyone give me any example of a point that's on this curve? Um, let's say P is like some really large prime. Cool. 1, comma 2. Are there any other small? Oh, can anyone give me some other example of a point? Are there other small valued one? Sure. Okay, well, that's fine. We'll just go with 1, comma minus 2. And I don't actually know off my head if there's any things that are just solutions of the integers, but because we're taking mod P, you could imagine, like, for example, if P was, if, all right, I'm gonna have to wing this. 8, um, oh, geez, I should have prepared an example. 8, 5, 4, 3, 3. If P, for example, if P is 197, you can verify that A comma 11 is another example of a point on this curve because you get 515 is congruent to 121 mod 197. So I just want an example that has larger numbers. Okay, and the thing that you need to know about this elliptic curve, there's two things. One is that there is a commutative addition on it. So theorem, um, given 2 points on the curve, what I can do is I can take the line through these points, imagine taking them and intersecting the curve again at another point here, and then taking the reflection of this point across the axis like that. So if I have 2 points A and B, you can do A plus B. This point is what we call A plus B. So it turns out, and this is kind of the black magic of elliptic curves, so I'm not going to talk too much about it. But there is a way to add 2 points on the curve AB to get another point A plus B. And this plus is associative and commutative. Right. The other thing is that I'm going to pick my curve, and I won't tell you the details of how you can do this, but I'm going to pick the elliptic curve, which I'm going to give it a name now, call it E. You can pick the prime P and the elliptic curve E such that the curve has exactly Q points on it. So I'm going to rig it such that the number of points on the curve is supposed to be a prime number. All right? What else do I need to do? I went to pick one particular point on the curve O, which, for those of you that know what these words means, it's at infinity. If you don't know what those words are, it's okay. We won't actually use this. Um, but the point of the point O, pun not intended, is that it's going to be the identity for this operation, meaning that A plus O is A, which is also equal to O plus A. So what have I told you up to now? We have a curve E, which consists of some points whose coordinates are mod P. We have an addition on it, which is associative commutative, and whose identity element is a particular point called O. So I haven't told you how to do this addition efficiently. I've kind of given you this picture just for purposes, but the important thing is that there is an addition operation, and in practice, it can be computed pretty efficiently. Like if I actually gave you some points and I asked you to compute it, it's like there are ways that we know how to do this. And finally, I've rigged it such that the number of points that is in play is exactly E. And it turns out what happens is that the addition on the curve E turns out to coincide basically with integers mod Q. Um, Meaning that if I take any point and on the curve and add it to itself Q times, I go all the way back to the identity 0. More explicitly, if I pick a particular any point other than O, you can imagine that E can be thought of as P. So let me use O first, and then P, P plus P, P plus P plus P, and so on, all the way up to Q minus 1 copies of a point P, and then the addition is exactly the way you think it is. So at this point, I'm even going to give these things names. I'm going to call them 0p, 2p, up to Q minus 1 times P. And my head is definitely blocking the curve. Yeah, let me move that. So actually, I'm going to hide the picture because this picture is not really that important. So the part that I'm going to take as a black box for this lecture is that we're going to have an elliptic curve, and there's going to be Q points on it, and the addition structure looks exactly like what you've seen when you do like number theory questions on like the AMC when you're taking stuff mod Q. This is what's going to happen. I've taken the integers mod Q and put a very elaborate operation on them that sort of resembles where it's possible to do addition, but it's a lot more complicated than the addition you learned. But if you squint at just the coefficients of P, then all you're doing is working with the integers mod Q. Um, is that okay? Does anyone have any questions on what the API I'm calling is? So again, we have a curve, and then I have a bunch of points on it, and then what I do have is like a way to add the points together, and that addition looks like mod Q. Okay, that's fine. So what's the kind of point of this addition is that there's a couple properties that it has that just like, why did I have to do all this work to the elliptic curve to get another copy of Z mod Q, right? There's sort of a couple of new things that I have that weren't true before. So one thing is that if I have P, you can find, let's say, what was a good number? What is a number that isn't too, let's say 100. You can find 100p with fewer than 100 addition operations. So I've told you there's an addition that you could implement on a computer if you want. It's like a little expensive, so you don't want to do it way too much, but you can do it. I claim that if I have a point P, I can get you the point 100p without having to use the addition function 100 times. In fact, you can do it in, let's see, 五六六 should be like 7 or 8, I think. And this uses a trick that's really similar to repeated squaring. Um, if you've seen like the math contest problems before, where let's say you're trying to compute like 3 to the 100 mod some large prime, like, what's a big prime? Uh, I don't know if that's actually prime or not. The reason it's called repeated squaring is because it's the same trick that you use to compute, let's say, 3 to the 100, where rather than like taking the number 3 and multiplying it a bunch of times, you keep squaring it instead, where 3 to the 100 is 3 to the 64 times 3 to the 32nd times 3 to the 4th. And so you can get these things a lot more easily because all you do is you take the number 3 and keep squaring it until you get the right power of 2. The same thing happens with elliptic curve addition, where if I want to compute 100p, 64p plus 32p plus 4p, I can do it by repeated doubling, where I compute 2p, which is p plus p. I compute 4p, which is 2p plus 2p. 8p, which is 4p plus 4p. All the way down to 64p, which is 32p plus 32p. And now I have this thing and this thing, this thing. So as promised, by only doing the addition operation 8 times, I can get the value of 100p. So 8 is a lot smaller than 100. Yeah. Um, to do a related example, I guess, like if I wanted to do 150p, say, um, can someone tell me how to do it and how many addition operations I would need to get 150? Yeah, okay. So you take the 128, 16, for 2. And so, it takes 7 addition operations to get all the powers of 2 up to 128. And then you pay 1, 2, 3 more addition operations. So what this means is even if your number is really, really big, like you can imagine there's some like, 30-digit number here. Even if you have an enormous number and you need to compute like an enormous power, it's actually just okay. Like we don't care. Because 30-digit numbers might be big, but their log 2 is only going to be like 100-ish. And if a computer doing something 100 times, that's kind of what computers are meant to do. So because of repeated squaring, we have the first thing, which is that it's easy to compute. I'm going to introduce a new notation. Whenever I write the brackets around n, I mean at n times the number p. But there's also another flip side to this, which is that it's really hard, it turns out, to find n given bracket n. So if I give you a number, you can do this multiplication really quickly. But if I go the other way and I give you the point on the curve that you get n times p and ask you what was the value of n, there's no good way to do this currently known. This is what we call the discrete logarithm problem. For those of you that like this Olympia number theory flavor, it's like if I ask you to solve the equation 3 to the x equals like 17 mod some very large prime, if p is like the 100 digits or something. This is really hard. No one actually knows how to do this efficiently. So even though for any individual value of x, I can guess it quickly, going the other way turns out to be basically impossible. Like we don't know how to do the reverse of this bracket operation. Unless you have a quantum computer, in which case, yeah, go for it. But I don't think we have quantum computers yet. I haven't been following the state of the art on that. So if you like, the bracket is already almost like a hash. Like the bracket is sort of this new is already a hash function where we do, but they are pretty bad. Yeah. Did we get what's the biggest number we've managed to factor? Because I know the hype about yeah, the hype about quantum computers is that they can also factor things in not polynomial. Um, they can factor numbers in a way that classical computers can't. But right now, for practical reasons, we just don't have them. We can factor the number. Chat says we factored up to 21. Like quantum computers can apparently factor the number 21 now. So it's still a ways to go. But in theory, they're faster if you ignore the implied constants and all the engineering concerns, because that's what mathematicians do. Uh, cool. There's one more thing that I need to get out of this. So up until now, what these brackets does is brackets is basically a hash. But because we've defined it on this elliptic curve, there's things that you can do with brackets already that you can't do with the normal hash functions. For example, if you have hash of n, if you have bracket n and you have bracket k and you want to add them together, you can actually do that now. So if I have a bracket n, bracket k given to you, you have no idea what n and k are, but you could compute n plus k, for example. So because this is like really cleanly defined working mod Q, like the math for this bracket is much nicer than the math for something like SHA-256. There's one more thing, which is that there's something that's called a pairing, and you can verify if you pick Ewell. And this is some very, very advanced algebraic geometry that's way above my pay grade. But if I give you bracket A, bracket B, and I might only need this up to bracket C, I think, where A times B equals C. So again, if you give you these three things, you have no idea what A, B, or C are. Like the brackets are hiding. If you put a number in the brackets, nobody can see it. But from these points, it turns out you can verify that the underlying numbers A times B equals C is true. So you have a way to verify A times B equals C, even if the numbers are in brackets, even though you can't access any of the numbers A, B, and C individually. Some of you might be curious already, and the answer is no. We don't know how to get. If I gave you bracket A and bracket B, we don't know how to go from bracket A and bracket B to the bracket AB. Unless you know the underlying numbers A and B that are hiding inside. Once I commit the number A and B inside brackets, if I only give you those points, we actually don't know how to get the product. But if I tell you also the bracket product, the relevant word for this is called the Weil pairing. There's a thing that is called the Weil pairing, which allows you to verify that A times B equals C. In fact, okay, let me check my notes to see if I need the higher level version. I don't think I ever use. Yeah, I'm just going to use AB equals C. So these are the three properties of the elliptic curve thing that I'm going to use in addition to the fact that there's integers mod Q, which is that when I actually give you the points, the bracket serves as a one-way hash, but the additional property that you can do addition because it's just A plus B. So if I give you bracket A and bracket B, you can compute bracket A plus B by just adding the 2 points together because these are points on a curve. You have a way to verify multiplication even if you can't see the numbers inside or compute the multiplication yourself. Addition is fine. You can add two bracketed points and get A plus B bracket without knowing the underlying A and B. Cool. So addition is fine. All right. Does anyone have any questions up until here? Okay. That's fine. So this is all I'm going to do with the elliptic curve setup. Now I can finally tell you the KZG protocol. Okay, so in order for this protocol to work, what we need to start is we need one person that we can really trust. So I don't know. So I need a name that's like, okay, Victor. Yeah, Victor gets to. Okay, Victor gets to be the trusted person. Um, so Victor is going to set up this protocol for us, and the way that he's going to do it is he's going to pick a secret number S. So Victor has this number S in the integers mod queue that nobody else knows. And what Victor's going to do is he's going to compute all the following numbers. So 1, S, S squared. So really, like, Victor has this laptop, all right? How do I draw a laptop? That knows the value of S. So maybe, yeah, it's probably better if I draw it like this. Oh geez, art is really hard. Here's Victor's laptop. Victor's laptop knows the value of S, doesn't tell it to anyone, and then posts the values of 1, S, S squared, and S cubed, all the way up to however many things we think we'll need. Let's say S a million to be safe. So yeah, Victor's number computes all of these 1 million points on the curve and publishes all of them somewhere where anyone can see them. All right. And once you do this, you do something really important, which is take the laptop and you throw it into the ocean. Yeah. Pretend that's like an ocean or something. I don't know. Okay. As soon as you finish publishing these numbers, we need to really make sure nobody ever gets the value of S. So, throw the computer into the ocean. I don't know if the Dallas Circle will reimburse you for the laptop. You can try asking. We'll find out. Uh, well, we post these numbers in, and that's the one-time setup. Once we've done this, we take these posted numbers, and then these are our points. Okay, so now we can bring back, what was the guy's name again? Warren? Yeah, Warren. I don't know why I drew a hat. I just like it. So what I told you is that I need a way for Warren to commit to some polynomial p. So you imagine Warren has like some polynomial p in his head that only Warren knows. So here's a polynomial, all right? Let's pretend it's like x squared plus 5x. And the way that you do the commitment is that you take the polynomial and you evaluate it at the secret number s and publish that. S squared plus 5s is the commitment. This is our definition. And you might say like, wait, but you told us that nobody knows the value of s. So how is Warren supposed to compute this? And the reason is that we've published all of these things up here. So the definition of the commitment is that it's like the polynomial evaluated at s. And the reason that you can compute this even without knowing the value of s is because all these powers of s got published on the internet. So what Warren would do in this case is he would take s squared and then 5 copies of the number s that were published, add these things together on the elliptic curve, and that's the commitment. And if I only give you this thing, you have no idea what the values of you have no idea like what the polynomial is because you don't have a way to even get the value inside, and even if you could, you don't know the value of s anyways. So that's not a proof for those of you that are like, very carefully following. This is just kind of heuristic argument that like, if I only have this bracketed thing, I can't get the number and also the number is useless to me. So with just the commitment, fulfills the property that it's binding and with that it's hiding, which is it hides the polynomial s. Hides the polynomial p from whoever's looking at the commitment. But I also promised you that I could open the commitment at any point, and I'll show you how to do it for 1 point, and then I'll show you how to do it for 1,000 points. So suppose Warren wants to say, all right, I have this polynomial. I've published this commitment somewhere on the internet. So you can say this is a published commitment. Let me point to just. Let's say that Warren wants to convince you that P of 1 is 7. So Warren would like to convince you that he doesn't want you to know anything about the polynomial. It could be x squared plus 5x. It could be x plus 6. It could be the constant polynomial 7. It could be like, I don't know, x cubed minus x plus 3x plus 4. But I'm going to convince, Warren wants to convince you at least P of 1 is 7 and tell you nothing else about the polynomial P. So I want to open the polynomial commitment at just that 1 point. So what Warren's going to do is he's going to take his polynomial, P of x minus 7, which I guess in this case, anyone see the mistake I made? Oh, jeez. I'm sorry, 1 plus 5 is 6, not 7. Um, I was like, why is this polynomial not reducible? It's supposed to have a root of, yeah. So because P of 1 is actually 6, this polynomial x squared plus 5x minus 6 is going to factor, right? Um, oh, jeez. How do you factor this thing? It's like x minus 1, x plus 6? Now I wish I picked a polynomial of higher degree. I want to change the example to x cubed plus 5x because I want the other factor to not be linear. So, then we have Wolfram Alpha open or something. Can someone tell me how x cubed plus 5x minus 6 factors? Uh, x squared plus 6x. All right. Plus 6, right? I hope. Is that right? That doesn't look right. Sorry, it's, oh my God. X squared plus x plus 6. There we go. I think that should work now. Yeah, that's fine. Okay, cool. So basically, the idea comes down to this. The following identity is true. P of s, which was the committed value, minus 6 is going to be equal to, because this is an identity that's true as polynomials, it should be true when I plug in x equals s. And it should be the case that s minus 1 times s squared plus s plus 6. And I changed the example, so let me update the picture here. This thing is going to be true in the sense that the pairing operation that the V pairing operation that I was talking about earlier will allow someone to verify that this number inside times this number inside is equal to this number inside, even without revealing any of the numbers. And so Warren has already published the number on the left-hand side because this number side was the commitment and 6 is public information because 1 is publicized. S minus 1 is also public information because Victor computed these things for us. And s squared plus s plus 6, again, the point is that this is also public. You have to look up the table now because but the point is everything in here is sort of public now. So in order for Warren to convince you that P of 1 is equal to 6, All he has to do is tell you my proof is that I have this s squared plus s plus 16, which is the quotient. Warren can compute this using the published information too. The verifier can see it as well. And Warren says, my proof that p of 1 is 6 is that the polynomial I claim p of x minus 6 is divisible by s minus 1. And maybe I'll just throw in s minus 1 in here. And here's the factorization using the published information. So if Warren sends these two orange things to you, you can verify his proof by verifying that these things are computed correctly from the published numbers, and also that the Vey pairing verifies that this number is this number times this number. So even though nobody in this whole thing knows anything about, oh crap, hang on. Sorry, let me back up. I don't want to decompose this. Warren wants to not reveal anything about the polynomial. So, I mean, this is true, but what Warren says is just s squared plus s plus 6. So he doesn't tell you that it happens to be made out of those things. He only gives you this particular thing. S minus 1 is fine. But don't reveal the polynomial is a quadratic polynomial because, for example, Warren doesn't want you to know it's a cubic. So, yeah, sorry, let me fix this. I think I would just want to say this. So Warren says p of 1 equals 6, says that out loud, and my proof is that I can give you this bracketed number. I'm not going to tell you anything about how I got the things inside this bracketed number. It's just I'm going to give you this thing wholesale. So Warren can compute it because Warren knows the polynomial and can do the polynomial division, but he's going to do the polynomial division for us and only send this entire thing. So this is the proof. And then this one is this one here, and this one here, and this 6 here is this 6. So this bit and this bit are all public information. This is the entire proof. Warren doesn't let you see how it's built. He only gives you the output. And it gives way for Warren to do polynomial division indirectly. So he can prove to you that p of x minus 6 is divisible by x minus 1, which is good enough to convince you that p of 1 is equal to 6. So this is how you can do one value. Now, if one wants to do two values, for example, here's Warren again. This time, instead of saying that p of 1 is equal to 6, he says p of 1 is equal to 6, and then p of 2 is equal to, oh god, what's p of 2, someone? Make sure I don't mess this one up. 18, I think. Is that right? Someone check my arithmetic. Is it 18? Yes, cool. All right. You can do basically the same thing where instead of dividing by x minus 1, you divide by x minus 1, x minus 2. So what the computation is you take p of x and you subtract off a linear polynomial that passes through these two things. So this one's going to be like 12x minus 6, I think, is the one I want. So this is at 1, this is 6, at 2, this is the 18. And so in order for Warren to prove this to you, Warren needs to prove to you px minus 12x minus 6 is divisible by x minus 1, x minus 2. Now, Warren knows the polynomial p, so Warren can do the division himself. And jia jiu san x plus 3, I think is what it turns out to be. So even though Warren is trying to prove two elements, his proof is still only one element. He will compute the quotient, evaluate the quotient at S, and send this as his proof. And then now we can do basically the same thing where P was already published. This 12 times S plus 6 can be everyone can compute this because it's built out of the published table. Everyone can compute S squared minus 3S plus 2. And then Warren's one-line proof, the single element S plus 3, gets stuck into the equation here. And for this proof to work, the verifier verifies that the Vey pairing correctly checks out on this multiplication equation. And so now I've done this for 2. And the way you can do it for any number of points is that instead of 12x minus 6, we fit a line through these. If you have 1,000 points, you fit a degree 99 polynomial through it. And do the same thing. Warren does the division for you, takes the quotient. The proof is just this one element, that single 256-bit number, and it lets you verify simultaneously all of the opening claims at once. Okay, and then that's it. All right. Um, yeah. All right. I'm also exactly at time, so we're going to pretend I timed that exactly right, even though I was totally winging it. But I'm not going anywhere, so I also have time for any questions as people want to ask them.
All right, thank you so much for the talk. If people have questions, feel free to put them in the chat. I know people had also submitted questions through the registration Google form, so
Oh, okay. Yeah,
those
feel
are
free to
more
fire those.
general.
Yeah.
But if people have questions about the talk itself, then put them in the chat.
Cool. Yeah, while we're waiting on questions also, I should mention that all of this stuff is written up if you want to see it. I'll paste a link into the chat of this thing that I've been writing where if you want to see this thing written out in full, it's chapter 3 of this mini textbook thingy-majiggy.